Hi everyone. So in today's session, I'll be taking you through a very popular probability distribution, which is the Poisson distribution. Okay. So let me just clarify as to when is it used. Poisson distribution is normally used in a couple of instances when we know the average rate, okay, of occurrence of events, right, in a specific time interval. In a time interval, okay. So when we know that the average rate of the interval average rate of occurrence of events in a specific time interval is lambda etc., then we can use this. So that is one. Second is when the events are independent, okay, events are independent. All right. And the third one is when the probability of occurrence of events, okay, occurrence of events in a very small span of time, in delta t is close to 0. Okay, this is when the Poisson distribution comes in handy. So the examples could be, number of phone calls in a call center. Okay, this would normally follow a Poisson distribution, okay, in a call center. The second example could be number of vehicles, okay, passing through a specific signpost, okay. So these are examples of Poisson distribution cases wherein we know that the average rate of occurrence of events in a specific time interval is what, right? That could be calculated using the mean, etc. Then the events are independent. One phone call in call center is independent of the other call which we get, and the probability of occurrence of those events, right, in the small time frame is 0, sorry, is close to 0. Now how do we start deriving it? So we start with something called as a binomial distribution, okay, which says that the probability of success in n trials, okay, is given by this nck, okay. So what does this mean? It says that the probability of success is n trial. N is nothing but the number of times you actually do something. For example, you throw a coin, right? So let's say if you throw a coin 10 times. So what is the probability that 8 out of 10 times you get head, right? So for such type of questions, we use binomial distribution, in which say, okay, nck is nothing but the number of times in which k events happen. So 10 would be, n would be 10 in this case. Number of times a coin is thrown and head turns up, and 8, right, because 8 times is the head coming up. Let's say it's slightly biased coin and the probability of head is 0.4. So it would be 0.4. How many times we need is 8, and then 1 minus 4 is 0.6, and minus k is nothing but 2, okay. So this is the simple binomial distribution, in which we are saying that the number of times, the probability that a particular event happen, n number, k number, specific number of times, which is k in this case, is given by nck, pk because this is telling the probability of event happening, and we want to happen it to happen 8 number of times, so it is 8, and 1 minus p is nothing but the probability of failure of the event, which is the tails coming up, which is 1 minus p, and n minus t is, and minus k is nothing but the number of times. Because these are independent, therefore we can multiply it separately and we end up getting as this. Okay, so let's go to our case. In our case, we are talking about Poisson distribution, and as I said, what we tend to do is we divide the time interval, okay, into many small pieces, t1, t2, t3, t3, t4, etc., till tn, and we are saying that the probability of the event in each of these very small strips of time is close to 0. Okay, so what we are saying is we have n, right, which tends to infinity, and then we are saying the probability of occurrence of the event in the small interval of time is p close to 0. Okay, and we said it is lambda. So lambda is nothing but the average rate of occurrence of events in the entire time span, which we already know. Okay, so this is what we already have, and then what we tend to do is, let me increase the space. Okay, so now I'll come back, and then what we are also saying is, because np is equal to lambda, therefore we have p is nothing but lambda by n. Okay, Now let's go back to our formula. So binomial distribution says that the probability of occurrence n number of times when you do the trial n times is nck p raised to the power k into 1 minus p raised to the power n minus k. Okay, so let's put the value. Before we do that, let's expand this. So nck is nothing but n factorial into n minus k factorial into k factorial. This is from combinatorial maths. And then p, let's replace this by lambda by n raised to the power k. Okay, and then 1 minus lambda by n raised to the power n, and then 1 minus lambda by n raised to the power minus k. Now this seems to be very daunting. To be honest, this seems to be very daunting. So let me try to simplify this stepwise. Let's look at this friend of ours on the extreme right. Okay, so what we are saying is 1 minus lambda by n raised to the power minus k. Okay, so what this becomes, sorry, I'm having trouble with the mouse over here. All right, that's good now. So when n tends to be very large, n is million, etc., n is, let's say, 1 lakh, so it becomes 1 minus a constant number, which is lambda by very huge number, right, 10 raised to the power 6 or 8, etc., in which case this tends to be 0, right? So 1 minus 0 raised to the power minus k, which is nothing but 1 raised to the power minus k, 1 raised to the power anything is 1, right? So we can discard this. This is almost equal to 1, so we'll let it go. So we are left with these all parameters as of now. Okay, now let's try to simplify this. Let me try to simplify the second term, which is 1 minus lambda by n. So let's assume it to be 1 minus lambda by n. Okay, let it to be y, and then we say, okay, ln y equal to n ln 1 minus lambda by n. Okay, now how do we simplify this? We simplify it by having a look at the graph. Okay, so if you look at the graph of ln x, how does it look like? The graph of ln x looks like something like this. Okay, now I'm putting, this is 1. Okay, now if I put it ln 1 plus x, ln 1 plus x, so what the graph would be? The graph would shift by 1, which means that the graph becomes something like this. Okay, so nothing but ln 1 plus x. Now if I do 1 minus x, which would just be a mirror image of this. Okay, so this becomes ln 1 minus x. Now the point to be noted is when x is very small, right, when we are close to 0 and x is very small, so in this specific part, right, this ln minus 1 minus x tends to be minus x, or generally when x is very small, then ln 1 plus x tends to be x itself. Okay, so we'll use this proper algorithm. So let's say ln y, sorry, okay, ln y we have becomes over here, if we go, and ln 1 minus x, so it becomes equivalent to n into minus lambda by n. Okay, which becomes equal to close to minus lambda, and therefore y becomes what? E raised to the power minus lambda. Okay, so how did we arrive at y is equal to e raised to the minus lambda? Again, reiterating, we had a look at the graph. So if you look at the graph of, okay, I will try it once more. You look at the graph of y is equal to ln 1 plus x, right? It will be something like this, and thing to be noted is in very close place, right, in very close space, this very close place over here, yeah, this tends to be close to x, right? So ln 1 plus x becomes x, and therefore we can write ln y equal to n ln 1 minus x, which is nothing but n minus lambda by n, and then y equal to minus e raised to the power lambda. So then we are left with, so this is also something which we have written. Let me bring my, okay, where is the more? This becomes e raised to the power minus lambda. Okay, so we have resolved this. So we have got rid of this, we have got rid of this as well. Now this is the piece which is remaining. Okay, so let me sort this out as well. So we'll write it as n factorial by n minus k factorial, okay, by n raised to the power k. Okay, so let's try to get rid of this. So how can we write this? N minus k factorial. So let me write it as 1 into 2 into 3, 3, 3 till n minus k. Okay, factorial. This takes care of n minus k factorial, right? But you see, we are writing n factorial, right? So n factorial is what? N factorial is 1 into 2 into 3 into 4 into till n minus k factorial, and eventually we need to reach at n. Okay, So if we are subtracting this n minus k, it would be something like this. If we are subtracting k from this, it would be something like this: k minus 1, n minus k minus 2. Eventually, this would become n minus k, okay, which would be n minus k is nothing but n, right? So you see, I'm just trying to decompose the n factorial such that we take care of n minus k part, and then we also see it that okay, if we continue with this, what is left? So what is left is n minus k minus 1, n minus k minus 2, etc., etc. Now the interesting thing to note over here is how many such terms are there. Okay, how many these terms are there? So if you look at this, this is simple. So you see k minus 1. So this is the first term, this is the second term, until now, or we have k terms. Okay, so overall there are k terms over here. So let me go back over here and write. So this could be written as n minus k factorial, okay, into the same thing, n minus k minus 1, n minus k minus 2, okay, till n minus k, okay. And then we already have n minus k factorial over here, so this would cancel out n minus k factorial, and then we are left with n raised to the power k. All right, what next? What next is this thing. So what we do is, let's take n out of here, so that becomes 1 minus k minus 1 by n. Okay, then again you take n minus n out of here, so it becomes 1 minus k minus 2 by n, and then eventually it would become 1 minus k by n, okay, by n raised to the power k. So you have a look at this, k minus 1 by n. Now n is very large number, as I shown, right? 10 raised to the power 6, 10 raised to the power 8, etc. So this would tend to become 0, because any constant by a very large number would tend to be 0. So this would eventually be n into 1 minus 0, n into 1 minus 0, till n into 1 minus 0, right, by n raised to the power k. And as I said, these number of terms, okay, are nothing but k times, okay. So n gets multiplied k times, so it becomes eventually n raised to the power k by n raised to the power k, right, into 1, etc., etc. So this also get cancelled out, so this becomes 1. So eventually the PMF of, let me go back to the PMF. What was the PMF? We had written this, right? So this was the PMF. Let me again write it so that become very clear. N factorial by n minus k factorial into k factorial, right, lambda raised to the power k by k factorial, and then we had e raised to the power minus lambda n, all right. Lambda, just remove this. So this we already sorted out. This becomes and also there was n raised to the power k, right. So this becomes, just let me remove that. This is what I said becomes 1, and the other things remain as they are. So it becomes lambda raised to the power k by k factorial into e raised to the power minus lambda. Now this is the PMF, probability mass function, right, of the Poisson distribution. And where it comes handy is the use cases which I was talking about, number of phone calls. So assume the number of phone calls which we have is 5 phone calls per hour in a call center. Now what we want to find out, what is the probability that we get, let's say 10 phone calls per hour, okay. So what we'll do is, we'll just use this formula, lambda is what we are saying 5, so 5 is the average rate, and we want 10, 5 raised to the power 10 by 10 factorial into e raised to the power minus 5, right. So this is the probability that you will get 10 calls per hour, given that the average is 5 calls per hour, okay. This was an example. Now let's talk about the mean and variance, okay, mean of Poisson distribution. So we know the mean of any distribution which is discrete is given by this, okay. Now how did I write this? This is easy to understand. Let's assume you have a dice, okay, and you roll it in number of times, okay. So for example, let's say we have die 1, the probability is 1 by 6, we have the number 2 is 1 by 6, the other thing which is 3, this probability is also 3 by 6, etc. So when we find the mean of this, okay, what do we eventually do? Mean of the die throwing. it becomes the number which the random variable will take multiplied by the corresponding probability, which is nothing but 1 by 6. Similarly, the value that the random variable can take multiplied with the probability, right? So on and so forth. So the same way we are writing over here, the mean is nothing but the values which the random variable can take, right? So k goes from 0 to infinity multiplied by its corresponding probability. So this is how we define the mean. Okay, now let's get back to this. So we have k equal to 0, infinity, k raised to the power lambda raised to the power k by k factorial into e raised to the power minus lambda. Now what? Now what can we do? So what we do is a manipulation. So what we do is, let it write lambda this, let it write k only. So what we do is we write k minus 1 and then we write k factorial as k into k minus 1 factorial. The entire idea is how do we get rid of this k? Okay, so k factorial can be written as k into k minus 1 factorial, but then in order to bring this into the format of standard Poisson distribution, the power of lambda also should be equal to what is there in the denominator, right? So therefore we did this, and then because we are writing lambda k raised to the power k is lambda raised to the k minus 1, so it should also be multiplied by 1 by lambda such that k minus 1 plus 1 becomes lambda raised to the power k over here, right? And then we write e raised to the power minus lambda. Okay, so this becomes k equal to 0, so infinity, this gets cancelled out, we are left with this. Okay, and because we are left with k minus 1, so it should be 1 lambda into e raised to the minus lambda. So what we can do is take lambda out over here, put it over here, and then we have this nice expression. Okay, now what is this number? This is nothing but the probability mass function summation over infinity, and as we know, the sum of all probabilities, right, multiplied by sum of all probabilities multiplied with the corresponding number tends to be 1, right? So this is what I'm saying. If you look into the area of this graph, which is nothing but a distribution, over here is normal distribution, right? So if you sum this up, right, the probability across this area, this becomes 1, so this would also become equal to into 1, right? And therefore this becomes lambda. So mean of Poisson distributions become equals to lambda. Now what about the variance? Variance is also interesting. So we'll use calculus over here, and the usage of this we would use several times in other derivations as well. So let's write, we know lambda is what, we just derived k is equal to 0 to lambda, sorry, infinity lambda raised to the power k by k factorial into e raised to the power minus lambda is what we know, right? Also multiplied with k. This is the mean. Now what we do is we differentiate it with respect to lambda itself. Okay, so what we get is this. Okay, so but first of all, why are we doing this? We are doing this because we want the variance. Okay, sorry, I forgot to explain as to why we are doing it in the first place. We want variance, and variance is defined as e of x square, okay, minus e of x, this entity, right? Now we already know this is lambda, nothing but lambda, right? We need to find out what is this. So what we need to do is, this would be nothing but, this would be summation of k equal to 0 to lambda k square into p of x equal to k, which is nothing but x square into this number, right? But what we know till now is, okay, let me also write what this would be, which would be nothing but k equal to 0 to lambda, okay, sorry, infinity k square into e raised to lambda raised to the power k by k factorial into e raised to the power minus lambda. So we need this, but what we know is till k only, right? So we derived just that k raised to the power lambda k by k factorial into e raised to the power minus lambda is lambda, right? So how do we get the k square? So one method is, if you see, we differentiate lambda with respect to k, then k would come over here, right? So we know this. So what we'll do is, see, if we differentiate with respect to this, so lambda would come down over here. So it would become k into lambda raised to the power k minus 1 by k factorial into e raised to the power minus lambda, right? So this is a raised to the power b. So when you differentiate that with respect to b, k would come down over here and this would be there, plus because we are applying the chain rule, right? So we are applying the chain rule over here, so this becomes the same thing, k lambda raised to the power k, and then we are also differentiating e raised to the power minus lambda, right? So e raised to the power minus lambda would be e raised to the power minus lambda into minus 1, right? This is by chain rule. So or what we are saying, 1 equal to summation of k equal to 0 till infinity is k square into lambda raised to the power k minus 1 by k factorial into e raised to the power minus lambda. And then if you look at this, okay, minus, if you look at this is what? This is nothing but the expectation, right? This is what we just derived, k into lambda raised to the power k e raised to the power minus lambda by this is nothing but lambda itself, right? So it becomes minus lambda, right? So what we are saying is, or 1 plus lambda equals to k equal to 0 till infinity k square into lambda raised to the power k minus 1 e raised to the minus lambda by k factorial. But what did we exactly need? We needed this entity, k square into lambda raised to the power k by k factorial e raised to the power minus lambda, right? We needed this because this is nothing but e of x square. So what we'll do is we multiply both sides by lambda. Okay, in which case it becomes k square into lambda raised to the power k into e raised to the power minus lambda by k factorial. Okay, this is what we wanted, right? This is what we wanted for e of x square. E of x square is nothing but this entity, k square this, and this is what we got. So let's now write variance is what? Variance is equal to e of x square minus e of square x, this entity, right? So just put the formula over here, which we have lambda plus lambda square coming from over here, and we have e of x, we found out it was lambda, now lambda square, because we need e raised to the power x whole square, so lambda square, so square gets cut and we are left with lambda, right? So the variance is also lambda. So in Poisson distribution we have mean as lambda and variance also as lambda, right? This is what we just derived, and the PMF, probability mass function of this, is lambda raised to the power k by k factorial into e raised to the power minus lambda. Okay, this is what the Poisson distribution is all about. And if I were to reiterate, the Poisson distribution is nothing but it talks about the probability of happening of k number of events, given that we already know that in a certain specific time interval what is the average rate of happening, right? So if lambda equal to, in the call center example, if we know that average number of calls which we get in a call center is 5 in a given hour and we want to find out what is the probability that in the next hour we get 7 or 8 number of phone calls, right? We'll use this formula. So what we'll do is we will write lambda raised to the power k to e raised to the power minus lambda by k factorial, right? So over here lambda becomes 5, k becomes 7 in my example, e raised to the power minus 5 by 5 factorial, right? So this is what the expectation is. What is the probability of you'll get 7 number of calls in the next 1 hour. So this is it. In my next session I'll be taking you through the other distributions as well. Hope you liked it. Let me know in the comments. Thank you.